Welcome everyone. Today we'll be doing time series forecasting, and this is not going to be a coding overview of time series forecasting and not really even like a theoretical mathy overview, but more of an introduction because time series forecasting is really nothing to be afraid about. I believe it's something very simple and that everyone can learn very quickly. However, it can get very advanced, and the more like theoretical math behind it is quite complicated. I'm sure that all of you are able to learn it. It's just that it's impossible to go over it in just 1 hour. And I want to use this 1 hour, as well as possible so you get the most out of it. And for this challenge, you don't really need to know, all the theoretical stuff behind it. So let me start the presentation, sorry. So yeah, that's 1 second. Yeah, so that's what the presentation is going to be about. Now, the specific things that we'll be discussing is, at first, what is a time series? Before we can forecast it, we have to define what it is, Some of you might not know it. Then we're going to be talking about, obviously, forecasting, the main three types of methods, I guess. Naive, exponential, smoothing, and ARIMA. Oh, we'll also be talking about decomposition before forecasting. And then I'll, share a few resources, and then we'll have a Q&A. And then also while I'm talking, please, if you have a question, I'm sharing my screen and I don't see y'all's faces. So if you have a question, please just unmute yourself and start talking. So, I can stop and you can ask your question and I can hopefully answer it. But if you have like a more general question about the challenge, stick till the end because you'll be able to ask me a question then. So what is a time series? A time series is just a data set that tracks a sample over time. So here I listed some examples of a time series. Pretty much, I don't know if you guys are familiar with this website. It's called the FRED. It's like our government website that tracks numeral, economical things, I rather say, not really financial products, but economical things. For example, like prices of eggs, which we have right here, or like, prices of milk, any type of product, or how many eggs are sold, anything like that. So all of those would be time series because you're looking at one specific product and you're tracking that product throughout the years, throughout time. So here's, we have eggs, and this, the y-axis is US dollars, and y-axis can be really any units, right? X-axis always has to be time, but y-axis can be dollars, amount, quantity, temperature, which we're doing, in the challenge in this case. But yeah, so here's some examples. Your specific height over time, or the average weight of an adult chicken over time. However, the one thing that I do have to say, something that's like, if you're measuring height over time, you either have to do like average height of all people in the US over time, or like one specific person's height over time. You can't just be jumping around and, 1 year you measure Bobby's height, 1 year you measure Joe's height, because, Bobby and Joe are not the same thing. So you kind of have to keep the actual sample the same. That's why it says here, it tracks a specific sample over time, right? So just a note on that. Let's go forward. So this is, once again, you probably saw this during the presentation that I made on Wednesday. This is the time series plot of the Datathon dataset, and you should be also able to get this plot when you run the code that I provided. So this is just a great way to see how the data actually looks like. And as you can see, it's not very, how do I say, like, it's not just a line. It has a lot of variation from time to time. It has, even though it looks like it just curves upwards, there's like this peak over here, like what's going on here? I'm not too sure. And that's something that you would want to explore with time series forecasting and just in general research, like why was temperature in 1950s over here so high? So the first thing that we'll go into and for time series forecasting is decomposition. So this doesn't necessarily even have to do anything with forecasting yet. So decomposition is just decomposing your data into trend, seasonality, and essentially remainder, or something that cannot be forecasted by trend or season. So the best way to think about it is just to look at this graph. So here we have a data set. And then trend is exactly what it sounds like. Is it like an upwards trend, a downwards trend? But it's not just upwards or downwards. It's more of like a very general curve of the data. It's almost like if you could, squint your eyes really hard, what would the trend approximately look like? Of course, here it looks like we can very easily, like you could have drawn this trend by hand, but the way that it does so like the reason why we use R or, any other, computer software like that is because it's not as easy as just, tracing what you think the trend is. There's a mathematical way to, extract trend from a data set. Now, seasonality is also something that it is exactly what it is, right? So it just basically means that your data has some trend that repeats over time. Examples of that could be how much power you use, right? Oh, sorry, I see I got a few messages. PDQ. Are we using private? We are all using the provided data. Yeah, we don't know external data. Please don't use any external data. You are forecasting on the provided data. Is this well, I will talk about PDQ for ARIMA parameters, but I'm not sure what you were exactly referring to because I just read the message right now. You can ask me maybe afterwards. As I was saying, seasonality, for example, energy consumption or like energy consumption throughout the years, right? You would imagine that there would be a spike in winter and a spike in summer every single year because more people use, AC during summer for use electricity during summer for AC, and then they use electricity for heating during winter, right? So there would be like an upward spike and a downward spike, and then during fall and like spring, it would be kind of, in the middle. So that's something like seasonality. And what you have in the end after you remove the trend and the seasonality is the remainder. And oftentimes that's what you actually end up forecasting on, because if we can just extract trend and seasonality, there's no point, running this entire data, this entire complex thing through like a forecasting process. We could just forecast on this instead, and usually you would get a much cleaner, much better forecast. This I want to mention, this is not specifically about decomposition, but you've probably, if you've taken like any economics classes or just in generally data classes, you've probably heard something called seasonally adjusted, which we can actually see here. We have the data and seasonally adjusted. All that means is that we've removed that seasonal aspect away from it. So it's like, but we kept the trend aspect. So it's like just data minus the seasonality. That's all that seasonally adjusted means. And another thing I wanted to know is that regular decomposition, also called classical decomposition, uses additive decomposition. So we add, we literally add the season plus the trend plus the remainder. So at every single point, we just add those values together. While in multiplicative decomposition, you multiply them. It's a little bit more complicated, and to mathematically actually derive it, it becomes logarithmic. But I won't go too much into that. So that's like just another graph of the decomposition, because in the previous one, the remainders they're lines instead of like being connected. But here you can see their remainder a little bit better. So yeah, after we just do STL decomposition here, we just forecast on the remainder instead. So yeah, like I've mentioned, classical decomposition is just additive, and it's the things that I've talked about previously. Now, STL decomposition, what makes it better is it's a seasonal trend decomposition using LOS. The reason why it's better is because with LOS, we're able to use essentially able to predict seasonality a lot better, because for things where seasonality is not constant or seasonality is not monthly or quarterly, we can't really, with classical decomposition, that doesn't really allow for that. So when we have some weird, seasonality, when it's like, 13 months or 22 and a half days for some reason. And of course, you won't really see that in natural data sets, but in some financial data sets, you might for some reason. For example, when I worked at RBC, since we used data that was business days, we would have a seasonality of 20 and 20 because there's on average 20 business days in a month. So that's why we would use STL decomposition versus regular decomposition. I've got another chat. Is forecasting based on... Yes, generally forecasting based on the remainder is better. Well, here's the thing, there's some models, they themselves take away the trend. So in the end, it might be the same. It depends on what model you're using. That's why you should even create like almost like a chart. So ideally, if you know how to, you should run like 100 models simultaneously and then compare their values, like whatever their error values are, and that's how you would be picking models. And then you can even combine models together, like you pick out the, out of 100 you get the 3 models with the lowest MAPE score, and then you can see how you can combine them, because when you average models you tend to get a better model in the end. Okay, the reason now the limitation of low-S is that it usually requires a lot more computational power. So when you're working on a data set, with thousands or really millions of data points, and it's not something that's too complex, you might be taking up a lot of resources. You might be, it might be taking you like a day to, go through that data set on your computer, when there's no need to do that if it doesn't, classical decomposition might have been enough. That's kind of the only limitation of it. But generally, if you can, which in this data set you can, this data set is pretty small, I would recommend using STL. Oh, I don't know why it's not. Okay, so now on to actual forecasting. So we'll start with the simplest one, naive. And so it'll actually be a little bit interactive. So naive forecasting, it's the simplest forecasting method. Simply set all forecasting to be the value of the last observation. So for example, tomorrow's forecast would be the actual value today. This method works very, very well on financial and economics data. I actually used it this summer, but it only really works good when your forecast horizon is 1, and I will show you here. So for example, on September 1st, whatever the value is, like it doesn't really matter the context of it, but on September 1st, the value was 2. So then we're saying, on September 1st, we're saying that the forecast for tomorrow, aka September 2nd, would be 2. And then we get 2, and that's what we like write down or whatever. Then on September 2nd, we say that we see that the actual value is 7. So then we're forecasting that, okay, tomorrow on September 3rd, the value will be 7, and so on. And just to, I don't know, to make it a little bit more interactive, what do you guys think would be the forecasted value for September 4th? What should we put for September 4th? I have like a question mark here. Yeah, perfect. Great job, Andy. Yeah, it's just -3. I know this sounds very simple, and it is very simple, but in like very small increments, especially when the data doesn't change as much, this might end up being the best forecast. And however, as you can see here, when you're forecasting for more than one time period ahead, so for example, for more than one day ahead, it will get, less and less accurate, because now you're saying that, on September 1st, you're making a forecast for the next 3 days, that, on September 2nd, 3rd, and 4th, it's going to be all 2, but that's really much like not the case. So it's a lot better when it's just like very small increments. Now, realistically, I would just tell you right now, you won't be doing this for our Datathon. It will probably be not a good forecasting model, but it's a good forecast to know. Now, naive seasonal forecasting, very similar, except now instead of just using one data point as kind of like the thing that you're copying, you're just using like the whole period essentially that you're copying, pasting all over and over again. So as you can see here for 2021, these are, we divided it quarterly, right? So we have quarterly seasonality. So these are the values for this year. And how we would forecast with naive seasonal forecasting is that we would just copy and paste that for next year. So quarter one 2022 will match quarter one 2021, quarter two 2022 will match quarter two 2021, and so on, right? So this is useful for very, very seasonal data, the one where, I would even say it would be great for something like perhaps like I can't even think, like the amount of candy canes sold during Christmas time, the amount of candy canes sold. So, I would assume that over the years, people only buy candy canes in December, right? So I think that would be a very highly seasonal data, and it doesn't really change from, year to year. I would say there's not like an upwards trend. It's just, it stays like that for the past, like, however many years. So that would be like a great example of using this. So now into SES, that's simple exponential smoothing. This is one of, along with ARIMA, this is one of the biggest things, how you can develop time series forecasting. Another thing I would like to note is that when we say something like SES model, we're not talking about just one specific model. It's not just one model with set parameters. You can change the amount of actual models you can create with it is millions, and you can do that by changing a few parameters depending on what model you're using. So SES is simple exponential smoothing, and it's, as it sounds, it's the simplest of the exponential smoothing models, so it's naturally called simple exponential smoothing. And what it does, it is essentially past observations are weighted with geometrically decreasing ratio. That's why it's like exponential, so it's like exponentially less. And the alpha value actually determines how much weight we give to the most recent observations. So to visualize this in the best way possible, I would make you look at this graph. So as you can see, the blue line is the actual values line. So that's what actually happened. While the green line is with alpha 0.8, and the orange line is with the alpha 0.1. So as you can see here, it's almost like very much smoothed out. It almost, we took like like a very general picture of it. While the green line pretty much follows the overall shape of it, right? So in this case, very much obviously, you wouldn't want to pick something with a very low alpha, but there are cases where you would want something with a low alpha. Another interesting thing about this, that if the alpha value is exactly 1, all it is a naive forecast. Because think about it, that means that yesterday's value is 100% important to our forecast. And what is naive forecast? Naive forecast is exactly that. All we do is we take yesterday's value. It's like the most important thing. We don't care about any other value. Yesterday's value, we give it 100% of our trust in it, right? And we make up tomorrow's value. And that's what's happening here. If we're saying that, yeah, we're giving yesterday's value 1, aka 100%. So that's another way to think about it. So it's like, a simple exponential smoothing value with a value 1 is just it's a special case, and it's also called the naive forecast. Now, Holt-Winters. This is, yes, Holt-Winters. We're actually talking about it right now. So perfect timing for that question. So this is, what happens is that there was that, simple exponential smoothing. I don't remember in what year, but Holt was a scientist and he essentially added trend to it. So now so regular simple exponential smoothing, it doesn't take into account any trend, any seasonality, but then Holt added trend. And Holt's model, when you just use trend, it's either called Holt's forecasting or double exponential smoothing forecasting. Now Holt-Winters came around, and then Holt and Winters worked, and they added another thing to it, which is seasonality. It's also called triple exponential smoothing. So To visualize it better, let's look at the pictures. So as you can see with Holt's method, that's the blue line, it just takes in the trend, right? So it had an upwards trend, so it would go up. That's what you would predict with Holt's model. Now with Holt-Winters model, you would use this on seasonal data. So we can even visually see that this has some sort of seasonality. It goes up and down at, approximately the same intervals. So we would use for this, but it also goes upwards, meaning that it has a trend. So we would use Holt-Winters for this. Another thing that I would like to add is that you might immediately be thinking, well, this, Holt-Winters looks like it's so much more advanced and so much better than Holt. Why would anyone even use Holt? Or, for example, simple exponential smoothing, it looks so much dumber, quote unquote, than Holt-Winters or than, just Holt. Why can't we always use just the most advanced model? And generally, obviously there's always a limitation of just how much computing power your computer has. So sometimes, like I said previously, it might be an overkill and you might be just wasting time trying to, compute with your computer this, much more advanced forecast when if your data just looks like this, it just looks like linear data with an upwards trend, why are you, wasting time trying to use this model on that? That's why you would just use the Holtz one. But that's just a side note. Yeah, so on to the next. Another thing is the damped trend Holt-Winters, or just Holt. What happens is that oftentimes Holt's and Holt-Winters models, they over forecast. They take they make trend too important, almost like too important to the model, and the trend will continue indefinitely. So for some things like population growth or GDP or something like that, it will just make the trend go indefinitely, as you can see here. But in reality, as we know, a lot of the data, a lot of statistics, they almost like asymptote, they like flat out. So in order to prevent that, these two people, they introduced the parameter called the dampness, and that essentially makes sure that the trend doesn't make the data go too too high up. It almost like cuts it off and it pushes it down, so it makes it more realistic. Cross-validation, I will not be going over this I will not be going over cross-validation and time series cross-validation and error calculations here. There's a lot of YouTube videos that go over that. This is specifically about time series forecasting. So there's many other methods, or I should rather say many methods that combine all of these things, right? They would like include they would include seasonality, but then not include something else. So there's a lot of like combinations that you can do, as you can see here. So the seasonal component, and this would be, I cut it off, but this would say like the trend component. So something would have an additive seasonal component, but then no trend component, or a multiplicative seasonal component, and then an additive trend component. You can make a lot of combinations. And obviously, like I said, there's not enough time to discuss all of them and how you would use, one in one case, one over the other. I just wanted you to guys know that they do exist, but most of the time when you're forecasting an R, you can set it on like auto select, so it will automatically select the quote unquote best one for you. For people that are a little bit more advanced and understand this a little bit better, I would say it's not always the best thing to do, because auto select is sometimes wrong because it prioritizes things that you as a person would not prioritize. And yeah, here's just like some of the notations and what like common colloquial names for that. So a method that has no seasonal component and no trend component, but is exponential smoothing, is just simple exponential smoothing. That's what we talked about for the first thing, right? and then Holt's linear method. Yeah, many. So a note on additive versus multiplicative. I've talked about this during the classical decomposition, but here it's additive versus multiplicative, not in a decomposition sense, but in actual forecasting sense. So an additive decomposition model is appropriate if trend cycle variation and the magnitude of seasonal pattern do not change over time, and with multiplicative is if they do change over time. So as you can see here, all of the seasonality and trend, it's approximately all the same, right? Well, here in multiplicative seasonality, this is the case where we would use multiplicative seasonality, right? As you can see, it's almost like it increases in like a bell shape or something like that. While here, it's visually pretty much constant. But these things, when you're actually working with data, there won't be as extreme cases like this. You won't be able to tell with your own two eyes whether I should use additive or multiplicative seasonality, right? So that's when you would have to literally run 9 of these, like all of these 9 different methods, and then using the various error metrics, determine which one would be the best for your situation. So now a note on ETS. So ETS it just builds on what we talked about. It's just error, trend, and seasonality. So now we just add error onto it. So we don't just make so we can also make the error not just regular, but we can make the error either additive or multiplicative. Okay, so now we will talk about ARIMA. Like somebody mentioned the different parameters of like P, Q, and D. So ARIMA is also known as the Box-Jenkins method. ARIMA stands for the autoregressive integrated moving average. And actually, it's a combination of multiple models. An AR model is a model that uses lagged values to forecast. And an MA model, moving average model, uses lagged forecasted errors to forecast. So when you combine these two models together, it becomes ARIMA, and I stands for integrated, and it consists of three parameters. Now, the assumptions for it is that it's non-seasonal, meaning that different seasons do not affect the values. However, there is a thing that exists that's called S-ARIMA, and as you might have guessed, S stands for seasonality. So if you do have a seasonal data set and you want to use ARIMA, just use S-ARIMA, which is seasonal ARIMA model. So it's not really a drawback of ARIMA in general, because you can make ARIMA a seasonal forecast. It's just that the regular ARIMA doesn't include seasonality, if that makes sense. And also, it doesn't deal too well with irregularity or, large outliers, which would be irregularity in your data. So things like COVID, or in economic sense, like recession. The parameters here, well, the parameters in the other one were the, how we're additive, multiplicative, and then we had also the alpha, which was the smoothing coefficient. Here we have P, Q, and D. P is the order of AR. It's the number of lags of Y to be used as predictors. In other words, if you're trying to predict June sales, how many previous lag months data are you going to use? Q is the order of the MA term, which is the moving average term. The number of lagged forecast errors. How many past forecast errors will you use? And D is the minimum difference period. So the minimum number of differences needed to take series data stationary. That's another thing. Another assumption of ARIMA is that it's a stationary data set. So already stationary data would have a 0 because we don't need to transform it into stationary data. So here's some benefits and drawbacks. In general, it's very effective and it's pretty flexible with data. So as long as it's time series data, univariate, and non-seasonal, and of course you can use S or ARIMA for seasonal, it should be generally good. but it has a stationarity requirement. You can read more in details when I post the presentation. Um, it, it could be a little bit tough to do model selection because you need to do various tests to pick out the exact values of these. And like I said, the auto selection in R and I'm sure in Python that exists is not always the best. So that's what makes it a little bit like not as friendly and harder to use. Um, I already mentioned stationary, but invertibility and invertibility means that the model's errors terms can be expressed as linear combinations of current and past forecast errors. It also doesn't work well with noisy data or data that includes things that don't usually happen. So like I talked about here, no irregularities. And then data length. So ARIMA needs a sufficiently large data set because it works with all data, while exponential smoothing models, they actually don't work with all data. As I've mentioned, this is best seen here. So actually, like I've said, if a simple exponential model has a alpha value of 1, it will only use yesterday's value to forecast. And the same goes for the rest of them. They just, add trend or trend and seasonality. But yeah, you have to remember that that is the base of them. So there might be like for SES, even if your alpha is 0.4, 0.5, depending on the data set, you might be only using the past 15 or 20 values or 100 values, right? So you can essentially even like cut your data off before then, before those, like it uses those 100 values. Well, for ARIMA, that it's completely different. It uses the entire, essentially the entire data set to make a decision. So here's some differences. I would say that even both of them potentially have infinite amount of models depending on which parameters, which alphas you choose. ARIMA models are all stationary, but they do have some overlap. Some of the ETS models and ARIMA models can be classified as either. Let me look at the chat. You can convert, so here's the thing, you can make a data set be stationary and then use ARIMA. And that might be better. It's very hard to tell just, how do you say this? If you know how to make a data set stationary, it's very hard to tell which method will be better until you actually test it out. It's like the same thing with seasonality. You might think that the seasonality is 12 or the trend is that, but the computer will always prove you wrong and tell you exactly what the value is, right? So I would say the best thing to do is just try it out. And also, this presentation was not meant to tell you this is what you should use for, the competition, or you shouldn't use this. This is not just a presentation for that. This is supposed to be a general intro to time series forecasting. And another thing I would like to note is that some of the things that I said might not be the most, like, I might have not introduced them in the most scientific, logical sense, if that makes sense. I didn't go into as many details because I tried to, fit this all into 40 minutes or so. So we're able to ask questions and stuff. But yeah, if you want to learn more, I would really recommend this website actually. That's how I learned time series forecasting. It's really nice. Really, obviously, you don't need any subscriptions. It's just a textbook. It's a textbook on time series forecasting, and it's really, really nice. But I want to wrap up the recording, and then I'll take any questions outside of the recording. So like I said, resources, this textbook is wonderful. These are a few websites. YouTube has a very bunch of like helpful videos and resources, and then ChatGPT helps so much to debug code and explains concepts very, very well. So if you still don't really know the difference between ETS and ARIMA, you could search up, hey, could you give me a few, differences, or in what case would I use this generally, and in what case I would use this. And yeah, thank you for watching. This is our link tree.